I don't know if he can like.
When he speaks, it will record it. Simple form definition, multi output regression. For start, let me give you a quick agenda. I'll start with the description of our exemplary measurement setup and the sending problem behind that. Before I briefly describe the error correction with a multi-layer perceptron that we showed last year at senders. After that, I show the error recognition that's new this year and the whole methodology before I close with some results and conclusion. So, for starters, our example application is the sensing of angular sending with magnetoresistive sensors. This is a contactless measurement found in many mechanical devices on many fields, primarily automotive and some industrial devices, where you have a magnetoresistive sensor, mostly XMR, EMR, EMR, MR, and so on, and an encoder magnet that rotates with position of a mechanical component. So the sensors, those sensors perform very well, but if there's a stray field, yes, here, those disrupt the measurement quite fairly and cause measurement errors of several degrees due to since the EMR sensor can be seen as an incomplete coordinate transformation. This is shown here. As you can see here, we have one encoder field, which shown in this direction. And if there's a stray field that can be in any arbitrary direction in any time strength, the sensor only sees the resulting magnetic field and is unable to distinguish. Is there a distortion, is there no distortion, and what I'm measuring. So our approach was from last year, we use not one sensor, we use a multitude of sensors, we use a sensor array, all measuring the encoder field at different positions. And this allows us for some alternative methods, numerical approaches, or in our case, signal processing by a neural network. It doesn't switch to slide, sorry. Oh, okay, so thank you. This was presented at the sensors last year, where we shown that we can correct the distortion by external magnetic fields, as well as calibration things with a simple multi-layer perceptron. And this small, rather small neural network approximates a correction function and learns the system parameter from a set of training data. All along, it's important to note that we always consider offline training of the network, since the measurement setup, if it's built, it's finished, and so we can keep the data set and do as many measurements as we like. So with this neural network, we can correct systematic errors such as misalignment between encoder magnet and sensor array. We can non-deterministic errors such as stray fields that can come and go at arbitrary strengths or from any direction. But there's a problem with this approach. If one sensor in our array fails, this error is obscured by the neural network, so we can't recognize such errors. This is shown here. I hope you can see that here's the blue line, our expected output. And here we simulated results for two different error scenarios. We have one is an offset of an angular offset of a single error from the array. As you can see here, it diverges quite a bit from the expected output, but it's in the general direction. And in the other case, we have a stacked error for one single sensor in the array, so the sensor gives always the same angular position. And now the results are all over the place. But the problem is, due to the neural network, it does a calculation as expected from the training data, and the output of the network is still in a valid value range. So we don't know if there is an error, or if everything is defined, or if there is an error. Since the neural network disguises the sensor. This is problematic in many cases. especially when you think of critical systems in cars or some industrial applications, you need to know if your measuring is correct or not. So our approach now is, since we only have the outputs of the network and the measurements directly from the sensor array, we are not directly able to recognize such errors. Instead, we extended our neural network to calculate additional wavelengths. So we extended this in that way that it also estimates the straight parameters. It gives us an additional information for to describe the systems, for debugging maintenance and such things. And now with this information, we can use to back calculate the expected measurements. This could be done by a numerical approach. Nevertheless, we choose here a neural network, since the network is able to learn the mechanical circumstances from the training data set. So instead, which would have been quite a big formula if we use it right in numerical. This is in setup simply looks a bit like an autoencoder. This is well known in the field. And sorry, it doesn't move. Oh, second. So the whole setup you can see here, we have on the upper side the network, the first network, it's the correction network. It gets the data from the sensor array. The network is trained, and the output is the corrected encoder angle and the straight parameters that we can use for further information. That's the actual measurement we want to use. And these values are feedback in another network that's trained to use the calculation in the other direction. And here we get an estimate of the measurements from the sensor array. And now we can compare those both values and see what we got. For the configuration, the correction measurement, the correction network had 3 inputs here. It had around about 300 neurons in the hidden layer, simple 2-layer setup, and sigmoid activation and linear output as a regression network. And the evaluation network has the same structure, 3 inputs. We needed a bit more neurons in the hidden layer, and also here sigmoid activation and linear output. We trained both networks separately due to on the one hand, this ensures that we can use a physical representation on the output, and it also reduces training effort a bit. And we use for this experiment shown here, we used a restricted training data set with 4 straight field magnitudes between 0 and 3,000 amps per meter from 4 different directions, all in the first plane. So this is the case. Here we compare the difference for one single sensor with the undistorted case. You can see here the difference when everything works fine. It's rather near 0, as it should be expected. And the high values here, that's the difference for a case with an offset, a 1 degree offset of 0 sensor. So we can, the distortion can clearly be recognize that there's something is wrong. We don't know what, but there's something wrong, and we can be sure use our results. Furthermore, this approach has another benefit. We can see if the input values are within the known range, in the range that the network is trained. And you can see here are some results for different straight combinations that were not directly in the training data set, but near the instances. And we have here always grouped in 3 colors are the straight magnitude, so 2.25 kiloamps per meter, 2.5 kiloamps, and so on. And red, green, blue are different angles of attack. And you can see here the 100 degree field, it's a green angle. We also see a high difference, and we can notice that this angle was not covered during the training set. So we can here give a bit of an insurance or if our results are reliable or not. So this was also tested with real measurements. So we had our automated measurement setup. You can see below here we have 4 large spools and physical encoder magnets that's rotated over the sensor array. The size is upscaled a bit, but the field magnitudes are like in the description by the sensor manufacturer, and the stray fields are according to the same simulation. You can see here we recognize in the green fields there's a training data doesn't match. Is not in the range that the network knows, and you can see here always at the beginning for each angle there's a bit there's a high difference. We had some issues in that range with the positioning of the encoder magnet. So in the first few angles, there was a bit of systematic error. That is, we're going to fix it in the next iteration. So that was all. I showed we adapted the MLP structure to recognize hardware errors. It can correct stray fields and mechanical tolerances. Additionally, we now can provide diagnostic information and recognize unreliable outputs and sensor faults. We verified this by measurements, and it can easily be implemented in a laboratory context, but for large scale deployment, the training is different. That was all. Thanks for your attention and